All right, everyone. Thank you for coming to this month's TNT seminar. For those who maybe haven't attended TNT events before, just a quick intro on the group. We are TNT stands for Translational Neuroengineering Technologies Network. We're a group, as the title says, interested in how neuroengineering technology and research can lead to translational applications. And we are a student-run group over multiple departments between BME, ECE, neuroscience, and clinical groups as well. So we're love meeting new people, and we put on a variety of academic, social, professional events. So 2 weeks from now, we're going to be having a journal club led by Rissa Shadmir on March 30th. And on the 31st, we're going to be having a recruitment event with Neuralink. So a lot going on. And if you guys are interested, we'll post in the chat our website link and the link to join our mailing list if you want to keep up with those different events. So as I said, we're very excited today. We're going to have Dr. Vikash Gilja presenting about brain-machine interfaces. He is an associate professor in the Electrical and Computer Engineering Department at UC San Diego. And I got to know him a little bit before I did my PhD, and he was a great mentor, very generous, and very willing to give great advice about different career paths and kind of how to achieve goals. So I owe a big debt to him, and very excited to have him join us today. So a couple things about the talk before we get started. One, Vikash said that he's happy to take any questions during the talk. So he asked that if you have a question, just use the raise hand signal in Zoom, and he'll kind of acknowledge that, and then you can unmute and ask your question. And so feel free to interrupt as needed. And the second thing is that we like to just kind of collect information for TNT. So sometime in the second half of the talk, we're gonna put out a Zoom poll to kind of collect information about you and kind of your interest in TNT. So please answer that and fill it out so that we can kind of, again, be in touch with you guys going forward. So with that, I'll let Vikash take over and lead the discussion. Thanks, everyone.
Thank you, Mark, and to TNT for the invitation. And I want to just circle back to some of the very nice comments that Mark made. We had some wonderful conversations years ago, and it's great to see him thriving in the PhD program. So again, good to see you, Mark. So I want to emphasize, I want this to be an informal conversation. That is my goal in the presentation. The slides here are just to support that conversation, so feel free to interrupt me along the way. I know you guys come from a variety of backgrounds, but I'm going to make some assumptions and move a little fast given the nature of the organization, TNT. But again, if anything's confusing, you want me to slow down, just raise your hand. It's more important to me that I've clearly communicated than to get through all these slides, right? Okay, so today I want to talk about brain-machine interfaces from a high level, from 50,000 feet, how we get from concept to clinic. And then I want to drop down to the ground and take a few deep dives with you on projects that I've been engaged in my lab. My hope is that I'm giving you guys a new perspective on BMI, but I'm guessing a lot of this is par for the course for folks in this group. First, I want to make sure I share these disclosures. I actually never thought I would have disclosures in my career. This is a testament to where neural engineering is going as a field. And again, I'm happy to talk about academics versus industry as well, and I'll stick around after if folks have questions. So what do I mean by brain-machine interfaces? Unfortunately, there's quite a few names for this technology, and there is quite a bit of confusion about these names. So I'm going to define what I mean here, but at broad strokes, a BMI is something that records from the brain, processes information and provides stimulation back. And that stimulation could be through the sensory system, or it could be through direct interaction with the brain. In particular, I think about and focus on brain-controlled prostheses. So these are systems that primarily focus on measurement from the brain, although you can stimulate to write feedback back in. But the systems that I'm primarily working with use the sensory system to feedback into the brain.
A sideways diamond?
And so in these systems, you might primarily be thinking about motor prostheses as controlling something like a computer mouse or a natural robotic limb. But more recently, there's been a lot of attention and new demonstrations of what folks are calling speech prostheses. And these speech prostheses, the way they're being designed at present, many of them, are still fundamentally motor prostheses. And I'll talk about that a little bit later today. But first I want to broaden back out, right? As we work on motor prostheses, my belief is that this technology has broader implications. And I'm guessing most of the folks here are familiar with the use of brain-machine interfaces for therapeutic stimulation. And technology that's been with us for multiple decades now is deep brain stimulation, which is approved in the US and internationally for a number of neurological disorders and diseases. And the core of this technology is to stimulate the brain and to measure behavioral output to calibrate that stimulation. But this process itself is hand calibrated, right? So you're measuring, typically a neurologist is measuring behavior, working with a neurosurgeon in concert to figure out when, where, and how to stimulate the brain to provide that therapeutic. And again, this is a technology that exists. It's reimbursable, it's purchasable, it can be done at UCSD. I know there's multiple DBS implants happening every week, and I'm guessing at Johns Hopkins, many implants as well. But what's the future of this technology? Many of us believe, and there are demonstrations of this now, of this technology moving towards closed loop or more intelligent stimulation, where we can pull the human out of, not fully out of, but partially out of the calibration process, and use recordings from the brain to directly decide on the stimulation parameters. And the core of this is what I call brain state estimation, right? We need to estimate the state of the brain to make decisions on how to provide feedback. And again, there are FDA approved technologies to do this. And many current clinical trials that are exploring these types of therapeutics. So I wanted to broaden back out because as we're working on brain state estimation for motor prostheses, my belief is that a lot of the core technology and techniques could translate to these other settings. So to talk about brain state estimation, we need to talk about brain recording methods. And I'm guessing this group is familiar with all of these techniques. Here today, I'm going to focus primarily on techniques that get closer to the underlying neurons in cortex. And so this would be intracortical recording as well as subdural electrocorticography. And if any of this terminology is foreign to you, just raise your hand and we can slow down right here. Okay, so good to go. Okay, so what do I mean by a brain-controlled motor prosthesis? So let's zoom in a little bit more. So typically this involves implanting electrode arrays. A very common electrode array that you'll see a few times today is the Utah array, which is shown here. It's about this size of the tip of your pinky. And from that Utah array, we record from tens to hundreds, depending on the style of implantation, of individual electrodes. And on each of those individual electrodes, we can get local field potential and action potentials. And the core technology applies signal conditioning and feature selection. So techniques in from signal processing are applied. And then machine learning techniques are applied to develop decoding algorithms that map recorded neural activity into intended movement, or in the case of speech, intended speech articulation. So one thing I want to highlight in the history of this type of brain-machine interface technology is that the Utah array itself is enabling technology. And a little bit of history here is that this device was actually developed at the University of Utah. That's why it's called the Utah array. It's developed by Dick Norman in the late 80s and early 90s. And then became commercially available. There's a long history of this company, BlackRock Microsystems, that if you're curious about, I can tell you more about after the talk. But the key is that this university developed technology is now commercially available. And there are multiple clinical trials that are going on with what's known as an FDA investigational device exemption that allows this device to be implanted for a year or more in individuals with tetraplegia. And this is what's allowed this field, it's enabling technology that's allowed this field to move quickly into the clinic. And so this is just a quick picture of a variety of motor BMI studies that are going on at present at different universities and research centers with this enabling technology, the Utah array. I want to highlight that 3 of these are happening under a research consortium called BrainGate that's growing, and I think officially there's a few additional sites that are being added in this month. So are these proof of concepts good enough? Yeah, and I think that's an important question, right? As we're developing proof of concept for brain-machine interfaces, I think it's important to pause and ask, where are we relative to the needs of the patient population that they're targeting? Back in 2015, we actually ran a survey of individuals with tetraplegia. And in this survey, we took a look at current implant technologies. We worked with a medical illustrator to develop these illustrations of what the implant would look like. And then we summarized what it would be like to have that device implanted and to use that device on a daily basis. And against that information, against each of these implants, we asked the individuals about their likelihood to adopt the technology if it could provide a specific level of functional restoration. And I recently took a look back at that survey relative to where the state of the field is now. And many of you might be familiar with a paper by Frank Willett, Jamie Henderson, and Krishna Shenoy that came out last year, demonstrating typing at about 90 characters per minute, 99% correct. So this is a major milestone in the field. So I took a look at that milestone relative to our old survey data. And it turned out that if we had wireless versions of the Utah array, the same technology that was used in this paper, the survey suggested that about 20 to 40% of individuals with high cervical spinal cord injury would opt for either a Utah array or ECOG grid-based implant. And I think this is, important numbers to pause on. And I want to highlight this word wireless. So if any of you here in this group are working on wireless technology, keep pushing on it, because it's a key enabling technology for individuals to adopt this technology. And so much so that in the survey, we found that the likelihood of individuals to adopt any technology, whether it was non-invasive or invasive, was heavily dependent on form factor. And the simple move to wireless, quote unquote simple, I know it's more complex than just saying go wireless, but that move to wireless increased the likelihood of adoption by 2x. So effort in that direction, well spent. With mouse control and hand grasp, which are current very active areas of research, and there are many proof of concepts. And these domains also had quite a bit of interest from that patient population. So things to pay attention to. Okay, so let's get back to these reporting methods and really focus in on what was done to develop neural interfaces. And I want to say I think it's a really exciting time to be working on brain-machine interface. And I need to share these disclosures again. But one of the reasons I think it is a really exciting time is because there is quite a bit of investment in new neural interfaces, right? As I mentioned, that Utah array that was developed in the late 80s, early 90s was a key enabling technology for all of the work that I very quickly summarized. But we have a range of companies now that are working on new neural interfaces that are taking ideas that started in the academic domain and hardening them so that they can become more widely available. And then there's also nonprofit collaborations like NeuroPixels that are providing technology that's very quickly advancing our capability, our measurement capability in the brain. And I think soon after we're going to see new capabilities on the stimulation side. So this is my little pitch, and I'm guessing I don't need to make it for this group, given that you guys are interested in neurotechnology. But this is the time to be in this field. And as those new technologies hit these types of trials, as well as the basic research that fuels the translation that's part of these trials, we're going to see advances quickly. So let's kind of focus back in on how we got here as a field. So I'm going to give you a very brief and admittedly very incomplete history of motor BMI. But this field really started out grounded in neurophysiology, and that underpinning has allowed it to become a field on its own. And that's how you guys exist as TNT, right? Translational neuroscience is a really important field now. And so how did this branch of translational neuroscience emerge? Well, we can go back to the 1960s, and I promise this history lesson will be really brief, but back in the 60s, Evarts demonstrated that neurons in primary motor cortex had a relationship to movement. And there he was dropping in single electrodes, measuring from neurons, and finding that moving versus not moving, you see changes in the underlying firing rate statistics. In the late 60s, Evan Fetz, who is still incredibly active, doing wonderful work in motor physiology and BMI, he provided the first demonstration of closed loop control, and he was doing this with single neurons, right? So he was recording from one or a couple of neurons, monitoring their spike rate and providing rewards back to the animal based on the firing rate. So he could get the animal to hit target firing rates based on this feedback control. And I believe this is the first demonstration of modulation control of neurons in motor cortex. Let's go to the 80s, where Georgopoulos and Kalaska demonstrated that these neurons that were recording in motor cortex were directionally tuned. So they had kind of this very canonical center outreaching task, and demonstrated that the firing rates that they measured were dependent both on movement, as Evarts had shown, but also dependent on the direction of movement, right? So here we're seeing rasters, spike rates from spiking from different neurons and different one neuron on different trials. And you can see that there's clear directional sensitivity. So this neuron prefers upward left movements in the simple task. And you can develop these tuning curves, right, to show that the firing rates are dependent on the direction of movement. And across the neurons that they recorded one at a time, they showed that there was a distribution of preferred directions, right? So now advanced to the mid 80s, and where Georgopoulos and Schwartz demonstrated that you could aggregate the activity from multiple neurons and predict reach directions, right? So this was a landmark study at the time. And this really, kicked off the field in many ways. We had the earlier work by Fetz showing single neuron modulation, and this recent, well, more recent, but now, over 25 years ago, study showing that if you have a collection of neurons, you can start to estimate more subtle details about movement kinematics. And this is really what drove the field of motor prostheses. And with this key enabling technology, the Utah array, we can now record from neurons in parallel. So we can make these estimates about movement kinematics in real time because we have parallel views, right? This is a key distinguishing point, right? This early work in the mid 80s was recording from neurons one at a time because that's the core technology that we had. But then as Dick Norman developed the Utah array, it provided a technology along with aggregate microwire grids that others were using around the same time, allowed us to record from many neurons at once so that we could fuel neural decoding strategies to build these closed loop systems. And things advanced very quickly from there. So here I'm showing citations in the early 2000s that that demonstrated closed loop computer cursor control. And the last one here is actually a demonstration with an individual with tetraplegia. And so you can see how quickly animal model studies in the early 2000s translated to studies in the clinic. Here I'm showing citations that were doing closed loop limb control, either robotic limb or simulated limb control. And again, we have citations that are quickly followed by human studies pointed to here in red. So you can see that these translations are happening within 4 or 5 years typically, getting us to this range of studies. And what I want to highlight here is that there's a motor prosthesis ecosystem that this field really benefits from, right? Where we have translation from basic neuroscience, neurophysiology, through to neural engineering, much of which happens in animal model, and then finally translational neural engineering that happens in the clinic. And this ecosystem allows for rapid innovation in the field. I'll just clear that annotation if I can. Okay, so let's talk about this ecosystem a little bit, and I want to pay homage to my advisors in my training, Krishna Shenoy, who is my advisor for PhD, and Jamie Henderson and Krishna, who are my advisors in my postdoctoral work, where I was first exposed to this ecosystem. And it's left a pretty strong impression on me and influences the work I do today. And during that time, I did have the opportunity to work with BrainGate to bring Stanford up as a BrainGate site. And so through that experience, got to see the power of this ecosystem from front to back. So how does my lab operate today? Well, I think of us as sitting squarely within neural engineering. That's the core emphasis of the lab. Day to day, we focus on signal processing and machine learning within this domain, but we'll kick up some embedded systems work when we need it to make experiments happen. And we interact heavily with folks on the material science and ASIC design side. So this work in neuroengineering really needs to draw inspiration, tools, and techniques from the basic neurosciences. And as a lab, we develop both behavioral and cognitive experiments to help design and validate our neural engineering systems with the overall goal of targeting clinical translation with our colleagues in the School of Medicine. I refer to this overall picture as a Venn diagram for applied neuroscience. I sit in an electrical and computer engineering department. So electrical engineering came from physics, physics became applied physics, and in many places became electrical engineering. And I really see a future for ideas coming from experimental and theoretical neuroscience, really pushing towards applied neuroscience. And there's a history of this, right? This is not new. But what is changing, and changing the last decade or so, is the rate at which the translation is happening. And that translation is really, based on iteration between basic neurosciences and neuroengineering that allows for rapid translation and feedback throughout these loops. So let's come back to brain-machine interfaces, right? So pontificated at a very high level now. So let's focus back down on this goal of brain state estimation. And so what do I mean by it? Well, how do we achieve this in practice, right? The brain has lots of neurons. Our current sensing technology is limited, but getting better, as I mentioned, and I think it's accelerating quite quickly. But this is still a massive subsampling, right? Even if current technology starts to scale by an order of magnitude every decade, it's going to take us, and that's very optimistic, but if that's the case, it's going to take us a long time to scale up to measuring from the entire brain, right? We need to be able to achieve these goals while still massively subsampling. And so how do we do this? Well, we focus on specific applications, simplifying tasks. There's a relationship between the complexity of output, of neural output, and the complexity of the tasks and behaviors that we're looking at, so we can model them as being a little more simple. We make assumptions that come from neuroanatomy as well as empirical studies that suggest that there is structure and redundancy in brain state. And when we start to consider multiple brain regions and start to look at communication between those brain regions, we recognize that those communications are bottlenecked, right? The connectivity within a brain region is much heavier than the connectivity between the brain regions in general. So high-level diagram, I figure credit from a paper by Gilja. This is a full schematic. So this is a small number of neurons, right? But think of it as a illustration of one small area of the brain. And these ends here that you see, N1 through 3, these are our measurements, so we're subsampling. The key idea is that the neurons in the overall population are highly interconnected, they're highly recurrent. And so we expect, although we're subsampling here, we expect there to be a lot of redundancy. And one of the key areas of theory that's advancing pretty fast in this field applies what's known as the subspace hypothesis. And the key idea is that when we look at neural activity within a brain region, we may be able to model it as living on a lower dimensional manifold within the higher D space of all of the neurons. So now, here in this case, I'm subsampling to 3 neurons. Within those 3 neurons, I might be able to visualize that most of the variation, most of the activity of those 3 neurons lives on a 2D plane. Now, for convenience, many of the mathematical techniques that folks apply assume linearity, so that's why it's a flat plane. More advanced techniques may relax that assumption and allow for nonlinear manifolds within that space. And so you can imagine at a theoretical level, you have these manifolds that may describe quite a bit of the variation within a brain area. And now we can start to study the geometry, right? The shapes of neural activity in that space, because we have this simpler description of neural activity. And we can also start to understand how those shapes interact between brain areas. So this is just a quick summary of some of the driving theory that we apply on a day-to-day basis. So now coming back to this question, how do we advance clinical neuroprostheses? Well, that comes down to augmenting our ability to estimate brain state in real time, and then applying those estimates to achieve goals. And I think of this as application-specific algorithm design, where again, the core problem is that we're recording from the brain. We want to make these estimates to drive different applications. And so today I'll take a few dives in the time that remains. I'll take some shallow dives in the non-bolded areas and some deeper dives in bolded areas. But I think of our work as falling within two categories. Thinking about probe design and optimization from a data-centric standpoint, and expanding our application space for using neural prostheses. And we study this expanded application space both in clinical settings as well as in animal model. And these are both areas of very active collaboration. So let's first talk about probe design and optimization and some work that we're doing with compressed sensing to develop neural prostheses. This will be a quick one-slide overview. There's a recent conference manuscript on this if you're interested. But one of the things we noted as folks are trying to really scale up the ability to record from the brain by adding additional electrodes and readout nodes is that power requirements generally scale by channel count. Now, this is at odds with this manifold or subspace hypothesis that I mentioned earlier. And what we're starting to look at is whether there may be strategies for improving this scaling. And to do so, we're looking at methods from the field of compressed sensing to develop hypothetical readout systems with the goal of sustaining our ability to estimate the underlying neural trajectory, right, the shape of neural activity that we can infer from the neurons that we record from. So we want to preserve that ability. We also obviously want to preserve the application-specific performance, such as motor kinematic decoding, as we develop these techniques. And so we do this by applying methods and insights from compressed sensing. And the key idea is that we want to reduce the number of channels while minimizing the reconstruction error loss. It's important to note that this idea has come about before in the idea of channel dropping. Here we are generalizing that idea to the concept of combining channels to more intelligently compress the data. And so to date, we've developed an unsupervised Gaussian process factor analysis-based channel compression strategy that you can read about in the paper. And we find that it outperforms the naive strategy that's typically used in compressed sensing, which is known as random projections, as well as another slightly less naive strategy that we've looked at. And what this technique that we've developed, which we call a conditional entropy-based technique, it allows us to have a negligible performance drop when we test against empirical motor data sets in monkey. When we test that, we have a very small drop in overall reconstruction loss or reconstruction error, and we can drop channel count by 50%. If we're willing to take a higher penalty in performance, we can go to 1/3 of the channel count. And obviously, there's a relationship between the number of channels we drop and the performance loss. Now, you might be wondering, why don't we just run the entire decoder and get kinematics out on the other end? Well, there's a tricky problem there, which has to do with generalization. And so by applying these unsupervised techniques, we can get better generalization to new tasks as well as to new task conditions than we would get with a simple supervised technique. Right? We want to sustain our ability to see the dominant neural trajectories while also holding on to our ability to decode kinematics. So if there are any questions about that, happy to field them at the end. I'm going to transition now quickly to one of the main topics I want to talk about today, which is developing high-density electrocorticography. And so to introduce this topic, I really want to have you think about two spatial scales here. We have the spatial scale of clinical ECOG versus the scale of that I mentioned before. So here's just a picture of an ECOG grid visualized on a 3D reconstruction of the brain, providing this for scale. So this is a standard adult grid that's commonly used in epilepsy monitoring unit. And let's compare the scale to those Utah arrays that I showed you before. So in those Utah arrays, the electrode tips are typically 400 microns apart. For this ECOG grid, the electrodes are typically about 1 centimeter apart. I should say 10 millimeters. Here's just a rough estimate of the size of the Utah array relative to the grid in blue. That's the Utah array for scale. But what I'm interested in knowing is what would happen if we drop the scale of electrocorticography to resemble that of a Utah array, right? So what if we were to pattern the electrodes with this similar hundreds of micron pitch and shrink down the electrode sites by orders of magnitude. So here we've worked with grids that have pitches between 50 and 400 microns. An important thing to remember here is the key difference between electrocorticography and intercortical arrays is, well, the intercortical arrays penetrate the brain to get the electrode tips close to the cell bodies, whereas subdural electrocorticography is sitting on the peel surface. So the individual electrodes are further from the cell bodies. So we've done this work in a variety of animal models as well as in the clinic. And I want to give you a quick summary of what we've been seeing as we've been increasing electrode array densities up to over 100 times that of clinical electrocorticography. So in one study that was led by a PhD student in the group, Nick Rogers, in collaboration with Anna DeVore, who's now at Boston University, we looked at high-level design requirements for high-quality electrocorticography, because if we want to shrink those electrodes down, we want to make sure we're doing so while getting maximal signal-to-noise in our recordings. So an obvious one here is we want low impedance, right? We want a good electrical interface to the tissue of the brain. Another one, if you armchair this, that makes sense, is that we want to be conformal to the brain surface, right? We want to get those electrodes as close to the peel surface, so they're as close as possible to the cell bodies that we're interested in. But one interesting thing that we found in both simulation as well as empirical studies is that the insulating boundary that the backplane of an electrocorticography grid provides, right? So the electrodes are in an insulating substrate. We found out that that insulating substrate provides an important electrical boundary at the clinical surface. So to describe this, imagine you have an electrode array with a solid substrate, as shown here. Well, you have brain tissue, and you might have CSF that sits between your electrode array and the brain tissue. Now you could imagine building that same array with minimal substrate, and folks have proposed this and have developed technologies like mesh electrodes that minimize the substrate that's present. And so these provide two different testing conditions. And what we found both in computational models as well as empirically is that these boundary conditions can increase by introducing this insulating layer. We can actually increase the amplitude of measured activity by 2x. And so those empirical measurements we actually made in rodent model with a whisker stimulation task. And we modeled these conditions by using a laminar array that gave us access to the recordings at depth and on the surface, and we could modify the CSF conditions by introducing an artificial CSF in our empirical studies. And we found that much of our result is consistent with prior finite element modeling studies that were focused on action potentials. Here we focused on high and low frequency ECOG and ECOG-like signals. Another obvious area that is important is durability and longevity, and I won't focus there, but if you're a developer of this technology, that's something you have to critically think about, as well as connectivity and telemetry, right? How are you going to get the data out? Referring back to those patient surveys I mentioned earlier, we need good wireless systems to provide fully implantable systems that are maintainable and desirable by patients and clinicians. So we went on, we also studied this type of probe. So in collaboration with Shadi Daye, my department, we worked with these high density PDOT-PSS based arrays that are in parylene substrate. So these provide many of those key features I mentioned on the previous slide. They are tightly spaced, 400 micron pitch with 30 to 50 micron diameter contacts, and very low impedance for the surface area that's being presented. Some of our testing was actually done in a songbird model called Starling, called the Starling model. The European Starling has really complex behavior. We'll talk about that in a little bit. But we did simultaneous recordings on the cortical surface as well as at depth using silicon probes. And we actually found in this particular animal model, and it's important to remember that this animal model, its neuroanatomy is different than ours. It doesn't have cortical layers, it has nuclei. So the architecture is different, but what we are able to demonstrate for the first time is that in this animal model, we could record putative single units from the cortical surface using these electrode arrays, and we're able to confirm the statement of single units by a few different measures. We looked at waveform characteristics, we looked at ISI violations, we also looked at cross-correlation between these putative single units that we are measuring at the surface. We looked at cross-correlation between those units and units that we were recording at depth using standard depth probes, this standard depth probe. We also took these devices to the operating room. This required quite a bit of development by John Hermes in the group and Nick Rogers. So they developed a set of custom electronics built on top of the Intan acquisition system and Intan chips by Reed Harrison. So we packaged those, added safety features as well as features that allowed us to handle the sterile dance between non-sterile and sterile areas, and ran studies in a pretty challenging environment because we were doing these recordings during awake neurosurgical procedures. And so we had to be pretty opportunistic in our strategy. And we could only add 30 minutes to overall surgical time, including any setup and experimental tasks that we were running. Important to note that this is awake neurosurgery, so that patients are brought up into twilight anesthesia. So in some of the cases, we're able to run simple behavioral tasks. So first thing we did was with Sid Cash at MGH was to do some comparisons to clinical electrodes. So many of these surgeries are being done for epilepsy mapping. And so there's an agent that can be introduced known as Brevitol that introduces ictal spiking. And so we took a look at the clinical standard electrodes, which you can see here, as well as our custom electrodes, which are hard to see in this picture. It's a saran wrap-like looking device that was recording in parallel. Shortly after administration of Brevitol, we don't expect to see ictal spiking, but shortly after, a few hundred seconds after, we expect to see it. And you can see that we're seeing activity both on the clinical electrodes, our own custom macro electrodes that are about the same size as the clinical electrodes, and our new micro electrodes that are 50 microns in diameter and 400 microns apart. And we did a number of comparisons of both the events of interest as well as looking at the spectral domain under the two conditions to understand whether there were similarities and differences between these different electrode types. From this human data, we also wanted to look at the nature of correlation between neighboring electrodes, because as you really shrink these electrodes down and bring them together, there is a concern that you're just measuring highly correlated volume conductance signals. And we compare this data to rodent model as well and saw similar trends that match our expectation. As we look at higher frequency components in the signal, we see that there is a faster fall off in the correlation coefficients. And we could actually model these correlation coefficients as a Gaussian process across the electrode space. So important to just kind of visualize this idea of volume conductance. If there's underlying signal sources that are spreading in space, multiple electrodes will get weighted sums of those sorts of signals. So natural question that we wanted to ask here was whether this higher resolution recording facilitates better brain state estimation. And so John Hermes led this work where we took these high density recordings during awake recording and asked whether we were in behavioral state 1 or 2. And we could induce these different behavioral states either by presentation of stimuli or asking the subject to elicit a specific behavior, like speaking a word, one word versus the other. Natural question about the underlying signal sources, right, in this volume conductance model is whether they're spatially broad or sharp. And so we started this activity in simulation. And in simulation, we showed that there are two conditions where higher density would improve brain state estimation. One was if the state dependent activity, the neural activity that's modulated by the state, if it's broad, but the state independent activity, the activity that isn't modulated by the state change, if it's sharp, if they're in contrast with one another, we see an advantage to high density. We also see an advantage to high density in these simulations in the opposite condition, where the state-dependent activity is very sharp, spatially sharp, and the state-independent activity is very spatially broad. We then took these simulations and tested them against our empirical data, where we were presenting different sounds to the subject. And so how do we do this test? Well, we have our micro ECOG grid. We could spatially subsample to develop subgrids. And what's critical is that under these two auditory conditions, we're seeing differential signaling. We primarily focused in the high gamma area of the signal. So to summarize that work very quickly, we are subsampling to develop virtual grids spatially, and then selectively removing channels to simulate a lower density grid. And this allows us to evaluate the promise of high density. If high density provides improvement, what we should see is that our state decoding accuracy, the distribution of state decoding accuracy should go up for the higher density grids versus lower density grids. And jumping to the punchline, when we look at the spatial activity between two auditory stimuli, we have a preferred stimulus and a non-preferred stimulus for these subjects. We could run these contrasts for different virtual grids where we're either looking at the full grid or subsampling down to 4 to a smaller number of electrodes, and we can do that in a few different configurations, different virtual grid sizes. And in all of these cases, we see that higher density is providing us with higher fidelity brain state estimation. So this is empirical evidence of what we expected from the simulations, that packing in additional electrodes, even at this fine sub-millimeter pitch, can improve our ability to ascertain the state of the brain. So let's scale this up. So again, coming back to my disclosure, so by interacting with industry, we're able to massively scale this up So Paradigmics had developed a system that allowed us to record from 30,000 electrodes simultaneously on sheep auditory cortex. This is a microwire-based device. Now, the way the microwires are bonded to the underlying custom ASIC that was developed by Paradigmics, that bonding process is imperfect, as you can see here. There's some random bonding that occurs. So this is showing all of the electrode points in space. You can see there's some gaps, there's differences in density. Just be aware of that as we're looking at the data. We measured in sheep, played sounds, similar to the human, different tones. We could record the response across those 30,000 electrodes. We get auditory evoke potentials. We can see those potentials across all of those electrodes. And then we can repeat a similar exercise that I showed you before with the smaller grids in human. In the sheep, we could see tone-topic organization as we'd expect in primary auditory cortex. So there's selectivity here based on region for tone. And then we could ask, if we placed virtual grids in different places, would we see differential error in decoding our tones? And we see that the blue spots are lower error, red spots are higher error. And so we could move these virtual grids around and subsample in various ways. And so we did that, and we also looked at the question of spatial coverage versus density within these very dense grids. And here's a summary of what we found. So I could change the spatial coverage from 1 square millimeter up to 90 square millimeters, and by subsampling, change the electrode count. To guide you here, these lines are lines of constant density. So along this line, we have the same electrode density, but we're increasing spatial area as I go from left to right. And in general, what we find is that even for very high density grids here at 100 micron pitch, as we increase spatial coverage, as we expect, the error goes down. But interestingly, for very small grids, we could increase density and reduce our error in estimating the playback sound. So this is an indication that one may be able to achieve equivalent brain state estimation with smaller high density grids relative to larger low density grids, which could have implications for the design of small, easier to implant brain machine interfaces. So I'll skip through this next section very quickly for a matter of time, but we also are working on neuroprosthesis design in the epilepsy monitoring unit. We collaborate with a wide range of clinicians across multiple sites. Very interested in analyzing free behavior. I'm going to just skip through this. An aspect of free behavior that we're looking at is behavioral context, which I believe is important for different BMI applications and generalization. So we have a paper on that. And we can also look at data across subjects. Here we've aligned neural latent space across multiple subjects by different shapes. The colors are consistent behaviors. This is a finger flexion task. Okay, so I'm going to spend a little more time on this last part, which is developing a songbird model for speech and vocal prostheses. And this is coming back to this idea of a research ecosystem, right? We need animal models for validation optimization of both surgical development and algorithm design. And this is, as I mentioned earlier, what I believe allowed this field of motor prostheses to translate so quickly. And what we're seeing nowadays is a real move towards real-time speech and vocalization prostheses. I think it's going to be a very impactful area in the coming years. We've seen some compelling demonstrations recently at UCSF and at other research centers. But the key idea, again, is to take brain activity, estimate intention, and produce ideally vocalizations, although most of the current examples produce text. But the key idea here that most of this technology is using is to still assume that it's a motor prosthesis. They're modeling the speech articulators, the tongue, the lip, the larynx, to make these estimates. And I think of this as a feedback control problem where we have the brain as the controller, and our job is to design using machine learning and control theory to design the right plants for this job. So how close are we to a true vocal prosthesis? I think this is an important question. The first example of a vocal prosthesis was actually published in 2009 by Gunther and Phil Kennedy. And there they were looking at tens of single multi-unit neurons in speech motor cortex and using that for real-time vocal synthesis. The only other real-time examples that we've seen are by Angrick more recently. Most of the work that's been done in this domain to get out to speech is all done offline. That's why my computer disk is there, and is done with electrocorticography. This includes these pieces of work. A key aspect of getting to closed loop is thinking through feedback delays, and the algorithm design and experiments vary. Why do we care about delays? Well, we've all experienced awful delays over the last couple of years in having meetings over Zoom, right? That 100 millisecond delay on Zoom is painful often to hold a conversation. Imagine that's what your speech prosthesis was doing. And so some of the work focuses on algorithms and techniques that allow for low delay, and these closed loop techniques are focused on very small delays, including some of the offline work. Just want to point to this very exciting work at UCSF by Amin Chali, which provides very relatively high fidelity outputs compared to other studies, but has delays out in seconds to achieve that higher quality. So these are important design considerations in building a system like this. Most of you have probably seen the recent New England Journal of Medicine piece from Eddie's lab. It's exciting work. It's a demonstration of ECOG from M1 in the speech articulator areas. It's the demonstration that this can be done, and it's mapping motor activity to words. It's applying a language model for error correction. I see this as a proof of concept. That's the main part of the study, that an individual that hasn't been able to speak for 15 years is able to use this system. But the system itself, keep in mind, is quite limited. It's a 50-word corpus, high word error rate, has really high latency. And if I apply my information theory background, my optimistic upper bound is about half a bit per second. And keep in mind that just the syllable content of human language, not including the expressiveness of language, has been estimated about 39 bits per second. My linguist colleagues tell me to take this as a lower bound. So we're clearly multiple orders of magnitude away. But if we compare this to intercortical array-based techniques, so that Willett paper that I mentioned before, I estimate that at about 6.5 bits per second. So maybe we're closer than we think we are, right? So that example gives me about 18 words per minute typing, open English vocabulary, right? If I had to choose a communication interface, I'd probably choose this one today. But if I put these two results together, I think the future is really promising for developing this technology. But we need more experience working with multi-electrode array recordings to develop speech prostheses. And we need to study this in a closed loop setting, very much like upper limb was done. And kind of going back to these studies in animal model, we need an analogy, we need an analogous system to do this for speech and motor prosthesis. And so what we've been working on is a songbird model. Why songbirds? They're not mammals, so there's some concerns there, right? This is an analogous system, not a homologous system. But the problem is that non-human primates have really limited vocal learning capacity. Birds are on this short list of complex vocal learners. So what they sound like, they have complex outputs, you can learn them. Certain species can learn them through life. Some of those outputs are complex enough to sound like human speech and language. It's also an accessible and well-studied species, right? Many decades of neurophysiology studies. And we can use this animal model to overcome limits in data collection that we have in the clinic: duration, electrode placement, fidelity of recording, right? Much more accessible in the animal model. And as you build these translational pathways, there's the personnel and trainees that benefit, that are able to cross this boundary, and you develop technology that can cross the boundary. And so this is what we're working on. And this is a highly collaborative effort with Tim Gettner. I myself don't have a background in songbirds until about 7 or 8 years ago when Tim and I teamed up. And so his experience in this area has been amazing. So what do? We collect naturalistic behavior from the birds, their singing. Their song structure is pretty complex. You can break it down into things that look like little sentences with syllables. We have a wonderful project scientist, Seke, who's developed a technique that allows us to implant neuropixels and record from multiple nuclei in the bird's brain. A nuclei called RA that's analogous to primary motor cortex, a nuclei that's called HVC that still debated about what it's analogous to, but perhaps similar to IFG in some of its nature. And we can hit both of these nuclei and record tens to hundreds of individual neurons from these nuclei during awake free behavior over courses of hours and days. So we've used these types of studies, this type of recording, to look at local field potential in the premotor region, HVC. And quick summary here is we see spectral components that are similar to human electrocorticography. This was actually quite surprising, so similar features. We can look at the structure of the underlying song and analyze the coincident local field potential as we do this. And we find that the local field potential is predictive of the vocalization types that we're looking at. And so if you're interested in this, you can read more about it in PlusConf Bio. Important thing, aspect of this song is that the vocalizations themselves are non-deterministic. If they were deterministic, we can't really build a neural prosthetic. You need some natural variation in the behavior. So there's differences in timing and structure with one of the species we work with, which is called the zebrafinch, which is very heavily studied. Tim Gettner happens to be an expert in another species known as the starling that has much more complex vocalizations that it learns throughout its lifetime, and we're leveraging this as part of our study design and development. So again, the LFP is predictive of both what syllable was produced as well as when it was spoken. And so again, more details in the manuscript. That LFP also gives us the ability to look at non-deterministic aspects of the song structure, so decision points, branch points. We can also synthesize the song from the premotor activity, and we're currently working on synthesizing from the motor activity, which we expect to be even more effective. But from the premotor activity, we can take small bins of spiking and run them through various networks, neural networks to synthesize song. And one of the things that we've done is we've built a system that incorporates the biomechanics of the bird's vocal tract as part of our song synthesis system. And we find that by constraining the decoder to these dynamics, we get more naturalistic outputs. And so this is just a quick summary. You can see the visuals here. If we introduce this biomechanical model into our machine learning strategy, we get much better spectrograms out. And the reason why the spectrograms of the biomechanical model look better than the recorded song is, well, when we generate this, we're subject to all the background noise in recording. So that's why the biomechanical model output looks like a cleaned up version. But if we decode from the LSTM or the feed-forward network, we get dynamics in the spectrogram that look very different than naturalistic song. And so you can hear these quickly. That's natural song. This is biomechanical model. Our LSTM output and our feed forward. So we think that these sorts of biomechanical constraints are going to be quite important for building learnable and usable speech prostheses. As I mentioned, we're recording this activity simultaneously across multiple nuclei. If we look at the motor cortex analogous area RA, we can apply similar transforms that are applied to M1 data in primates, and we can resolve neural trajectories. So this is an example of taking one trial of song and projecting into a neural latent space. We can do this for multiple renditions of the song. And so here's just a visualization of 10 single trials, color-coded based on the song syllable. And we can see there's quite a bit of consistency, even though the timing of the individual syllables is different. We see quite a bit of similarity in the trajectory. So we're currently studying the geometry of these spaces to better understand the constraints on the geometry. So again, just a quick summary of what I ran through today, and what are our next steps? Well, we're going to design, develop, translate, and repeat. That's what we like to do. So we're building out this feedback control system with the songbird. Along the way, we're studying the geometry of the neural state space. We're building a big repository of data for the research community. We want folks to share in on the terabytes of data we're generating from this project. We're starting to take this work and develop pathways to clinical translation, including the epilepsy monitoring unit, to share insights between studies. Along the way, we're designing novel neuroscience theory-driven readout systems, compressed sensing-based systems, and beginning to look at how we would develop multi-region neural prostheses to achieve some of the high-level goals that I stated earlier. So I want to thank collaborators and support. I have the pleasure of working with lots of people with diverse backgrounds, and I think that's critical for this type of work. And zooming in on my UCSD collaborators, it's really fun to be on this campus beyond the weather. And I'll make a little pitch here. We're currently recruiting a postdoc for research in the epilepsy monitoring unit. So if you're interested, just reach out. All right. Thanks everyone for sticking with me on this talk. Any questions?
Well, thank you, Vikash, for the talk. I think the review in the beginning was really insightful, and kind of the results you presented were really interesting, and you know, for me, very different than anything I work on. So I learned a lot. Yeah, so we'll stick around, I guess, for a couple of minutes if people want to ask questions, and if not, then we'll call it.
Hi, Vikash. So what's the latest, your thoughts on population spikes versus LFP versus ECOG?
Yeah.
Your opinion.
Yeah, so my current thought on it is, I think electrocorticography in general has been underexplored. Particularly high density electrocorticography. I think there's still quite a bit of promise that hasn't been validated yet. And I think work needs to be done there. I think overall for developing solutions, we're going to need a variety of techniques because the brain is not, it's not just a homogeneous piece of jelly, right? It has complex anatomy, and if we want to build systems that are going to take in information from many areas of the brain, we're going to need multiple techniques to get that information. I think at present, intracortical has empirically demonstrated, and we have theoretical underpinnings for this, has demonstrated a distinct advantage. I think the burden of proof is on the other techniques, right? But again, there's practical trade-offs in using one technique or another that have to be accounted for. Nitish, does that help or perspective-wise?
Politically correct, since in any case you're doing both, so I understand that.
Yeah,
maybe a follow-up. Go ahead.
And it's not meant to be politically correct. I think I'm trying to view this as an engineer, right? Which is any technology has trade-offs. And at present, intracortical, what we know theoretically, empirically provides higher information density. You can get to higher information density, but it's harder to implant. It's harder to maintain. Whereas, electrocorticography, depending on the size of the array, may be easier to implant under certain conditions, but can't give you access to whole areas of cortex. May be able to sustain its, may be sustainable over a longer duration. There may be some distinct advantages there, but is going to have lower fidelity from what we know.
Thanks. Nice work.
Thanks.
All right. I think with that, then we'll call it for today. Thank you, Vikash, again for joining.
Mark, I thought you did offer for Vikash to hang around for discussing trajectories, what he's been up to. So I wonder
Sure.
if some of you want to hang around, and some of faculty like me will just tune out, and you guys can have a friendly chat.
Sure.
About careers and career paths if folks are interested as well.
Sure. Yeah, I'll end the recording then, and we can make it more kind of informal.
Okay, bye then.
All right. Thanks,
talk.
everyone.